Good evening, everybody. Welcome to Modern Day Debate. Tonight, we're going to be debating gravity. And to get us started, we have Tacori. So thank you, Tacori, for being here, and the floor is yours.
Okay, good evening, everybody. My name is Tacori Dawson, and I am on the side that's opposing and on opposition against gravity. In my stance, I'm saying that gravity does not exist because of three reasons. It violates the laws of logic, and there's three different type of laws of logic. You got the law of identity, the law of non-contradictory, and the law of let me go to my screen. The law of the law of contradictory. So what is the law of identity? Two entities, X and Y, are identical if they share the same properties. A necessary insufficient condition of two entities, X and Y, to be identical, be the same, is that they share the same properties. So if X is not identical to Y or Y, I mean, it can't be Y. So meaning that the reason that gravity is an illogical thing is due to the fact that it has no real identity. It is a fact that, according to mainstream science, gravity is supposed to be mass attracted mass. But we know that there's another phenomenon that actually has that particular function, which is known as magnetism. So let's go to the definition of the term magnetism. So here's the problem. Magnetism is actually the force exerted by magnets which they attract, which is a pull force, or repel each other. Magnetism is caused by the motion of electric charges. What is gravity? Gravity is a force which a planet draws objects towards each other. So you got two concepts that has an attractive force. One is magnetism and one is gravity. We not on the opposition of magnetism because me and MCToon actually know that magnetism does exist. What's in the question of the day is gravity and whether gravity exists. And one of the reasons that gravity doesn't exist because it violates the first law of logic, which is identity, because it assumed the identity of other phenomenons. Let's go to another one. Gravity in our universe. Gravity is which hold planets together in orbit around the sun. Now, if you know what an orbit is when the sun or the moon or luminary bodies are supposed to revolve around another body. So where did this force come from? This force is called centrifugal force. Centrifugal force is a force as a net force in an act of an object to keep it moving along a central or circular path. In our article, the centrifugal force, we learned that any object traveling along a circular path, r radius and r velocity, r experience acceleration direct towards the corner of its path. This is centrifugal force, which has the same notation as gravity.
Just 1 second. I'm so sorry to cut you off. For some odd reason, Zoom crashed and it stopped streaming. I'm not sure what happened, so I'm just going to ask you to backpedal just a couple. I'm going to hit start streaming again. This is just going totally to plan, isn't it, tonight? Oh, boy. What happened on your end? Any of your audience say, was it just my face that was like, so sorry, guys.
No,
I'm so sorry, Tacori and MC.
I was taking notes.
Let me just try this up again here. We're going to make sure that we're back up and running. Let me just double check. Still buffering. Once we get back in it, guys, I'll let you know. It's just sorry about that. I did pause your timer there, Tacori, so yeah, if you can just try to pull yourself back like 40 seconds. I'm just starting the stream up again. There we go. Looks like we're back up and running. So sorry about that, everybody. We were just having a little technical issue. We're going to get back up into Tacori's opening statement. So Tacori, without further ado, let's carry on.
Okay, so back to what I was saying. One of the reasons that gravity violates the laws of logic because it has no significant identity. It has no significant identity, meaning that it takes the other identities of other phenomena, like centrifugal force, which is the orbital of bodies around another body. And not only just that, but the attractive force of magnetism due to the fact that gravity is a force that's supposed to pull objects to each other due to the center of mass. So now let's continue. Law number 2, the law of non-contradiction. X is not X, either X or not X is true, and either no is no possibility, meaning that it cannot contradict each other. The problem with gravity is that gravity is indeed a contradicting force, which means that it does not have the same consistent concept about the force. Let's give you a prime example. Gravity on the earth. Let's go right here. Gravity is a physical force of attraction on objects. Objects with a small mass have a weak gravitational force with those with a large mass and have a strong force. So pretty much the greater a force is on an object, the greater the mass is on an object, the greater the force of gravity is supposed to be. Meaning that gravity is supposed to be more effective on objects that got greater masses than objects that don't have greater masses. But this is actually a contradiction right here, because when you look at planets and you go to NASA.com, planets are the reason that, gravity is supposed to be the reason that planets are round, due to the fact that it exerts force around the whole body of the planet, pulling it to the center of mass. But hold on, wait a minute. We know when there's mass, there's supposed to be gravity. So the more mass that an object has, the more gravity it's supposed to have. So we could see all the planets is actually curved into a sphere because of gravity, right? Well, what do you got to say about the Milky Way? The Milky Way is pretty much a spiral, which is a central curvature over a flat surface. What is the mass of the Milky Way? The Milky Way is approximately 890 billion to 1.54 trillion times the mass of the sun, in a total of 8.9 times 10 to the 11 power to 1.54 times 10 to the 12 power solar mass, meaning that this thing got a hell of a lot of mass, more than the sun and more than the planets, but yet gravity ain't curving its Milky Way into a sphere like it's curving the other planets. But what happened to gravity needed more mass on an object to allow an object to be curved into a sphere, when we clearly see right here that the mass of this darn Milky Way is way greater than the sun, which is responsible for its curvature or its spherical shape due to gravity. But yet we see right here that we get a flat Milky Way pretty much. It's not even a spherical Milky Way, but according to the law of gravity, it's supposed to curve this thing into an actual sphere. So let's continue. So here's the law of exclusion of middle can be expressed by a proposition of formula P over P. It means that the statement is either true or false. That is, as it is claiming that there is no middle ground between being true and being false. Every statement has to be one of the other. That's why it's called the law of excluded middle, because it excludes a middle ground between the true and the false, or the falsified. The falsified. Now, when you pay attention to the gravitational force of the moon, the gravitational force of the moon is always going to be, the tides will always be more closer to the moon. I wish I could show y'all this model right here, but I can't even get access to my laptop because of the Zoom thing. But if anybody, any globe earthers out there that know they model about tides, the tides will be highest at the equator. But if you pay attention, it will have a descendant or ascending mount near certain parts of the equator to the part of the equator where the moon is directly at. This is not even real, because when you check out tide amplitudes, when you actually check out tide amplitudes, you have this thing called tidal nodes. And not only just that, but if you pay attention to tide altitudes, you can actually find that tide altitudes, you can find the highest tides near the coastline of different parts of the continents of the earth. But according to gravity and according to the moon's gravity and their model that they show, y'all show that the highest tides is always at the center of the where the equator is. But that's a contradiction, because that means that gravity is a selective force. So not only do gravity take on the form of other forces, gravity contradicts itself. Not only do gravity contradicts itself, but it's selective. I guess gravity is smart, and I guess gravity has the capability of having a decision where it want to just pick and choose what waters it want to put the moon. Yeah, what water do gravity want to pull up from the moon, and what water it don't want to pull up from the moon. Gravity is all of these things. This is why they try to make it hard for people to try to debunk gravity by embedding gravity into different concepts like magnetism, centrifugal force, surface tension, which is responsible for bodies of water being curved into a sphere, because the earth is supposed to be curved into a sphere due to gravity, because is it a fact that 75% of the earth has the surface of the water is 75% of the earth, and gravity is supposed to be bending all that into a sphere. But according to NASA, that's what surface tension is. It takes molecules of water and cluster them into a sphere, which causes bodies of water like a raindrop to become a sphere. That's my time.
Yeah, you've still got 30 odd seconds here on my side, but yeah, we can wrap up there. So yeah, thank you, Tacori, for your intro statement. Thank you as well, everybody, for being here. Sorry for the technical mishap. I'll do some quick housekeeping and we'll get right into MCToon's opening. So first and foremost, welcome to Modern Day Debate. We are a neutral debate platform hosting debates on science, politics, religion. We hope you all feel welcome here. I also want to let everybody know James is on his way to Mindfest. So if you haven't gotten your ticket for that, we still have the 20% off when you use the MDD promo code. So if you're going to be in Austin, Texas, and you can make it to the live event, we'd really like to see you there. And I'm sure it'd be cool to run into James, Destiny, and all the other great people that are going to be there that you see on Modern Day Debate. And secondly, one of our moderators, and you're probably familiar with them, has not been around lately and has undergone a pretty serious surgery. So we are going to tag Anathema's GoFundMe in our description here, and I'm going to put it in our chat for anybody who can help out, anybody who knows Anathema. He's done a lot of work to keep our space friendly, help source out other moderators, and he helps out with a lot of other channels as well. I'm sure, I think MCToon, you're also familiar with Shane Anathema. So if you have the means, thank you everybody who checks that out and supports our moderator there. So MCToon, over to you.
All right. Well, the standard let me yeah. The standard flat earth claim, which is the also goes along with the anti-gravity claim here, is the globe or gravity predicts, and then a thing that it doesn't predict, then this observation doesn't match the thing that the globe or thing that gravity doesn't exist. Therefore, flat or gravity doesn't exist. So that's the standard, most common argument. It's not always used, but it's very, very common. So the question is, does gravity exist? Does mass attract mass very specifically? So I have a video here I'm going to share from Stephen Mould, if you know who he is. He did a video on gravity. Is that showing there up on your side, Ryan?
Yep, you're up.
Okay. All right. So this is a university level apparatus for testing gravity. You can see the large sphere and the smaller spheres, and the smaller spheres are suspended by a torsion wire. And when you put the balls from one side to the other, it pulls those the small spheres on the inside toward the larger balls on the outside. And it's measured using this laser. You see this laser, it bounces off a mirror and then it goes up on this whiteboard here. So this is just demonstrating that gravity does in fact exist. And that laser will settle over on the right side. I'm going to jump ahead here so that you can see. And then he moves, he swaps the positions of the masses, and then it moves to the other side. So it definitely has been confirmed to cause the movement of those different masses. That's just kind of a demonstration that yes, gravity does in fact, or mass does in fact attract mass. Of course, that you might wonder, were there confounding variables at play there? Was there somehow electrostatics or wind or air movements or air currents or something like that? And you can see in the apparatus here, it's behind a little, there's a membrane separating them so that there's no airflow. There you can kind of see the reflection there. So there's no airflow. It's a sealed vessel on the inside. So air doesn't do it. They are all connected to the same electrical potential. They're all grounded electrically, so there's no electrical potential going on there. If there were any charge, they would all be at the same charge, either all positive or all negative, which is according to Coulomb's law, will be resistive. It would push the masses away from each other, not attract them. Yet they are attracting each other. So I'll jump here to a more precise measurement of gravity. This the BIPM measurements, the Newtonian constant of gravitation, G, and this particular one has significantly more controls on what is going on here. And here is the specific test masses here that they are moving in and out. And instead of this is cylinders, and then the smaller masses inside, you can't really see it, it's in the middle there, is actually a plate instead of spheres, so that they can more precisely determine the exact amount of attraction between them, which isn't really pertinent to this discussion. This discussion is, does the mass does a mass attract mass? That's a question at all. And of course it does. And this particular experiment confirms that as well. But I want to point out, if you want this, I have this on my website, mctoon.net/G. You can find this one. Just search for a BIPM. But this one has a particularly large there it is, the uncertainty budget that they talk about here. So where'd it go? So things like that they did is they used a particular material that's not susceptible to magnetism, and then they demagnetized it, which is they use hysteresis to demagnetize it. So we've got these two things that are not magnetized, or all of these things that are not magnetized. So it can't be magnetism that's attracting it. And let's see, do they have? Yeah, this is oh no, this one uses spheres on the inside. There's several different ones. That's why I got sometimes get a little confused. That's stainless steel. Stainless steel is non-magnetic. So they calculate the torque. Doesn't really matter all that much. The specifics of of how many digits of precision they got, a lot. It's that, is there mass attracting mass conformation? And the answer is yes. To move on the surface of the Earth, there is a downward acceleration of 9.8 meters per second squared, approximately, but it varies all over the Earth. And you can use the law of gravitational attraction and centrifugal force of the rotating Earth to predict the amount of the downward acceleration to a precision of 0.1% or more. I have a rather simple version of that on my website here if you want to just look for gravity predictions. I'll go over it really quickly. It uses the law of gravity. It uses the second law of motion. And you put those together and you solve for the acceleration due to gravity as g times the mass of the Earth over the radius squared. The radius squared then is the distance from the center of the Earth. And then we use the angular velocity here, the linear velocity, to get the centrifugal force. So that we apply out. We use this up, and we use this one to apply down. We put them together and we can calculate for any position on the surface of the Earth the specific predicted downward acceleration. So here's one in Hawaii. Here's the coordinates. Here's the elevation. The elevation matters. The distance from the center of the Earth and the tangential speed. So we use those. I'm not going to go over it in detail right here. If Tacori wants to go over the math later, we can. He's pretty good at math. So he's probably the best flat earther at math, I'll say. Tacori is probably the best. Gravitational field force there, that's what we covered earlier. The predicted downward acceleration in that spot in Hawaii is 9.77 meters per second squared. And then I have a list of a citation on here of the different measurements of it. And the measurement of it is 9.78 meters per second squared. A difference of just 0.012 or 0.13 if you round to two digits there. I have several others. We got International Falls. We've got Fortaleza, Brazil. Same thing. The predicted amount is very, very close to the measured amount. So when you have a measurement and a prediction that align, then that's a confirmation that your hypothesis is correct. And so this confirms right here the hypothesis of gravity. Or of mass attracting mass. I would love to see any flat earther present an actual prediction of the downward acceleration, the magnitude of the downward acceleration, using whatever it is that you think is the cause of the downward acceleration. I've never actually seen a flat earther even attempt that, like I just showed there. So, all right. How'd I do on time, Ryan?
Oh. Let's see. I got to unlock my phone. It's been so long I had to unlock it again. You still have... Oh, you're all out of time. Look at that. That's what it's saying here. I don't think you've gone on that long though.
Yeah, that's okay.
That's okay. I think you wanted to wrap it up there anyway, it sounds like.
Yes.
Um, that's cool. All right, sorry about that. Looks like my phone locked me out and my timer stopped, so I had to just kind of wing that one. You know how my math skills are based on our
Yeah.
pre-talk too, so
Yeah.
don't trust them. All right, we're gonna kick it into open discussion, everybody. So thank you everybody for being here. We'll do super chats at the end. So if you have questions for either of our speakers related to the topic, get them in now. Or if you just want to tell us that you think we look nice, that's cool too. We'll take compliments. So let's kick it into open discussion. And yeah, Tacori, I'll hand it over to you to respond to some of what you just heard.
Uh, Michael, you hear me?
Yeah, but I can't see you, buddy. I want
You
to
don't
see
need
you.
to see me. You don't need to see me.
All right.
I'm everywhere. No, I'm joking. Let me turn my camera on. I'm joking.
Okay.
Okay, I didn't know
Do
if
you
you might
see
have been
me now?
having some issues maybe with your data, but yeah, we can see you
We
great.
see it. We see it.
All right, go
Oh,
ahead there,
okay.
Tacori.
All right. Check this out. I need to question. Listen. Okay, you did the force times because I deal with this equation all the time. You do know when you do that equation, you do know that according to that equation, the same amount of force from gravity is going to be the same amount that is exerted on that person's body, right? It's the same weight, right? Of that person, right?
No.
No? Are you sure about that? Because I just did the calculation
Well, let's
and
see
put
it.
in some random numbers.
Let's
You can
see
even
it.
do
Yeah.
it yourself. Okay, let's check this out. You take the gravitational constant, which is 6.67 times 10 to the negative 11 power, right?
Yeah.
You take the mass of the Earth, which is 5.97 times 10 to the 24 power. That's sectotrillions. Let's say I'm 200 pounds, right? I'm not 200 pounds, but I'm just giving you a random weight. 200 pounds are 90 kilograms.
Okay.
You divide that into the distance, which is 6,378 square. In newtons, well, when you do meters, it's going to be 6,378,000 meters. You divide that, and you're going to get the mass. My body mass is going to be the same amount of force from that gravitational force. That gravitational force will have an exerted force of 200 pounds.
If you put in your mass and a different mass,
The mass of the Earth,
yeah,
which
but
is 5 point. Yeah, go ahead.
yeah, but the mass, like your mass of what would you say, 90 something, call it 100 kilograms and a mass of 200 kilograms will experience a different magnitude of force according to that equation.
We're talking about the Earth. That's why I did mass 1, which is 5.97 times 10 to the 24
Okay.
kilograms.
And so you're saying that the force between you and the Earth and you is the same?
It's the same as my weight.
Yeah, the weight and force are the same. So, yeah, that's the prediction. Yeah,
The prediction.
why is that? I don't know what's difficult
It's a
about
big
that.
problem. I'm gonna tell you why it's a big problem. Because we have every type of resistance. And it is not scientifically proven that a person really could just haul his own weight like that. Like it's not scientifically proven that somebody could treat a 200-pound person can treat 200 pounds like it's no weight. You know what I'm saying?
Oh
It's
yeah,
gonna
you
be some
can't
type
you
of
can't do
struggle.
that. Yeah, that doesn't
Okay, well
gravity
then
doesn't predict that.
then we could throw that equation away because that's based off the equation of gravity, the gravitational constant that you just showed.
I don't understand how you're trying to throw that away. What reason is
Listen,
that?
okay, it's the reason because you just agreed that the same amount of force that gravity is applying on a person is the same mass of his body, which is
No,
190 pounds.
force and mass are different.
No, listen. I'm taking them because newtons. You measure force with newtons, right?
Yeah, or pounds.
Yeah, but
Yeah.
they actually do it more with newtons.
Yeah,
And you
so
can
in
convert.
science we use newtons. Yeah.
Yeah, and you can convert 1 pound would equal like 2.25 newtons, something
Okay.
like that.
Yeah, there's a
Yeah,
conversion. Yeah.
Yeah, so I took 880 newtons, divided it by 225, and divided it by 2.25 or something like that, and I got divided it. I converted 880 newtons to pounds, which got me 190 pounds. So,
Okay.
meaning that me being 190 pounds, gravity would have to be applying a force of 90 pounds to pull me to the ground. That's based off that equation. I just
So
did that
wait,
equation.
let me try to understand. You weigh 190 pounds.
190 pounds.
And gravity would have to exert a force of 190 pounds on you.
Yes, based off that equation.
Yeah, it does.
Okay, so first of all, we don't feel at 190 pounds. I don't feel at 190 pounds. Well, listen,
if you jump, but if you jump, do you come back down?
We jump because we come back down to because of our weight. But based
exactly.
Off that,
weight.
We wouldn't be able to jump like that.
Weight is force. Weight equal force, right? So your weight is in pounds or in newtons. They're just different units for weight.
Okay.
So you do feel the 198 pounds because when you jump, you come back down. That's your weight bringing you back down.
No, we're not talking about my weight. We are also talking about the force that is being exerted. We are also talking about the force that's being exerted on your body from gravity.
Yeah, your weight is that force. They're the same thing. Where'd you go?
Hey, Corey, you're on mute.
Yeah, I'm hearing you. I thought you was talking.
Just your camera went off.
Oh, and he's on mute again. Are you trying to switch your system there, Tacori? You're still on mute.
Sorry about that, child. Sorry about that. I was trying to deal with my speaker real quick. I was putting in a new speaker.
You're installing speakers while you're having this debate?
No, I was just taking my headphone out and putting it in a speaker.
Oh.
No worries. Let's carry on. So if you want to refresh everybody where we were, either one of you, it's fine. We'll carry on. I'll hand it over to you, Mike, since you're not on mute. But
okay. Well, I maybe it's just a terminology thing. The weight that you are talking about, that weight is force. So they're the same thing. You're like, well, gravity has to exert weight on me. It does. Gravity has to exert force on me. It does. That's the same thing as weight. So
but here's the thing. Because an average 200-pound person just can't lift 200 pounds like that. They can't lift 200 pounds like that. They kind of can, but it's going to be they ain't going to have that much resistance.
Yeah, but I can bench 200 pounds.
But I mean, like, I'm not saying that it's impossible for somebody to bench 200 pounds. I'm saying that it's not going to be as easy as you raising up your arms and flapping your arms like a bird. It's going to be some pressure.
No, I don't flap my arms. I do not flap my arms like a bird when I'm benching 200 pounds.
No,
that's not the right technique, people.
No, listen. I'm saying that when I say flap the arms like a bird, I'm saying that that we ain't gonna have that high level of resistance to a point where it feel like that we only can feel a little bit of it, because an average human really. I mean, they can lift 200 pounds, but it's very hard for them to lift 200 pounds. You would have to constantly lift weights. It's not natural for that to actually happen. So it's not proven that
how about this?
Resist.
How about this? Do you think that a person who weighs 200 pounds could do a leg press of 200 pounds?
Leg press of 200 pounds?
Yeah.
They could, but they won't have that much. They won't have that much resistance. It would be like some type of struggle.
It would.
Because they're dealing with 400 pounds twice, like a 200-pound person would be dealing with 400 pounds total.
A leg press where you're sitting and you're just pressing forward, and it's 200 pounds that you're that
you put on your legs.
Yeah.
That's what I'm talking about.
Put your same amount of your weight on your legs, so you're doing only the amount that you already do when you stand up normally.
Yeah, that's what I'm talking about.
Yeah.
It would be your weight plus the amount of force.
Well, not plus, because you're sitting down. You're like pushing sideways.
I'm talking about gravity.
I'm talking up. Yeah.
I'm talking about gravity. Gravity plus our weight. We'll be dealing with
how much? Tacori, how much can you bench?
2 pounds.
2
I don't
pounds.
wanna
Oh,
tell
come on, man. You got it. It's all right, dude. You can, dude.
I
You're
ain't been
ripped.
eating
You're
my
ripped.
vegetables.
Just
You got it,
exercising
man.
the tips of your fingers. That's all.
I ain't been eating my vegetables like that. I ain't been eating my Boston baked beans like that.
Yeah.
Still in the pantry.
Dude, I like the Boston baked beans.
All right,
And
let's
then-
get back on
all right,
subject.
sorry.
Yeah.
It's
All right.
fine. It's fine. It's cool. It's
All
cool.
right, Tacori, I don't know if that's going too far, but let me do this. You said that gravity is magnetism, and I want to test that right now. I've got right here. This is a spirit level, but the bottom of the spirit level has a magnet on it. You see that?
I'm saying that it has the same concepts as magnetism.
Yeah. So here I have here a Phillips and regular bit, right? And it's iron, and that magnet there holds it. You see that? So that magnet is holding this bit. This bit is metal, and it's got.
So did
it's
it
got
pull
some-
it? Did it pull it? Did it pull it to the thing?
Yeah, it did. Yeah.
Okay, so
So
isn't
hold on.
gravity the same thing?
Hold on. I'm not done. Now I have right here a personal incredulity fallacy card that has less mass than the bit here. It has less mass, right? So now we're going to use this magnet, and we're going to have this magnet get pulled up to, or the card get pulled up to it, has less mass. So if gravity equals magnetism, then definitely this card will stick to
You're
the
not
magnet,
slick,
right?
bro. You're not slick, bro.
But it's not. Hold on.
Not
Hold on.
slick,
No,
'cause
it
that
was.
card
It's
ain't
totally.
magnetic.
Let me do it again. It's not.
It's not magnetic, bro. It's not magnetic, though, bro.
Corey, gravity is not magnetism. They're not the same thing. The downward
You
acceleration
ain't
is not
slick
due to
with that one,
magnetism.
bro. You're not slick with that
I
one.
don't know.
Nice try, though. Nice try.
I do
But
have
you're
the
not slick
personal
with that one.
incredulity card handy.
Okay, like I tell you what, take a smaller magnet, 2 smaller magnets, and let's see if it's gonna pull that. If that thing that you just pulled, that spirit level, if they both gonna pull it. See, one of them was magnetic and another one wasn't.
Exactly. So it's not magnetism. Gravity is not magnetism.
No, listen, bro. Listen, gravity doesn't. I know gravity ain't magnetism, but I'm saying due to the fact that magnetism attracts bodies to each other, right?
Uh-huh.
Gravity also attracts bodies to each other, right?
Yeah, it uses a different mechanism. Lots of things could attract bodies to each other. Dude, when you walk out on the street, Tacori, your body attracts bodies to you. Right? That's what I'm talking about.
You talking about when I walk towards?
No, I'm talking about all the ladies walking down the street. When you're walking down the street, they're attracted to you. Right?
That's
But that doesn't mean that magnetism doesn't exist just because Tacori attracts the ladies' bodies. All right?
All right. We don't need you guys flirting with each other. We're supposed to debate.
No. Now listen. So check this out. Let's talk about the downward acceleration of 9.8 meters per second squared.
All right.
Because remember, I beat you up on that already, though. Because
no, I have no recollection of you beating me up on that one. But
I know
let's go with it for fun.
But 9.8 meters per second squared. So meaning that every second the force will accelerate downward by 9.8 meters additional.
Uh-huh.
I know y'all use the 4.9 also. We could talk on that too.
Where'd the 4.9 come from?
Well, when Tony was talking about it on your show last time, he was talking about a 4.9 something, but if you don't want to talk about that, Tony, PhD Tony.
Oh yeah.
The one that got beat up by Wits on here. Sit on here.
Oh,
yeah.
Okay. Well,
listen, check
I don't
out.
know I don't know what this number is.
Let's let Tacori finish his thought there.
Okay.
But yeah, check this out. So that means that everything will fall at a 9.8 meters per second square, right? So meaning that every object, because you said it, I got the recording.
Well,
you said
let me qualify it. You have to control for confounding variables. But yeah, keep going.
9.8 meters per second square, meaning that every object in the world have to fall and accelerate at the same speed. This is not observable because I could drop a penny right now from my head to my toe. I'm 5'10", and a penny would take literally a whole second to hit from my head to my toe. That's 5 feet 10 inches, or that's 70 inches. That is not no 9.8 meters. 9.8 meters equals 32.15 feet.
Okay. But have you measured this actually, or are you just kind of going off the kind of a feeling about how fast it might go?
No, I literally counted. I know listen, I measured myself. I'm 5'10", and I counted Mississippi because that's how long it takes for you. That's how long the second is. Mississippi. It's a 4-syllable word. Mississippi takes 1 second. And from my head to my toe, that thing hit the ground, which means that penny traveled 70 inches per second downward. That debunks that 9.8 meters per second.
Tacori,
as a matter of fact.
Yeah. Can I respond to that? I think that the precision of your measurement apparatus might be at fault there.
What you mean, like
the precision of your measurement apparatus. So let me suggest this. Smartphones now do slow-mo, right? Super slow-mo, and they'll do 60 frames a second or 100 frames a second. So try this. Try getting something nice and high, as high as you can get, and then have somebody record it on slow-mo on your phone, and then drop it and see how long it takes to get to the ground. Do something nice and heavy, Do a car battery from the top of a parking ramp. That'd be great.
You know what? Anybody in the chat that is not biased globe earthers that hold on to gravity, do me a favor and take something just small. Just take anything. Just drop it from your head to your toe. Let the object go. Let it fall from your head to your toe. I know none of us is 30 foot tall. So drop something, take something, drop it down from your head to your toe and see how far would that travel and calculate how far that would travel. I'm pretty sure that's not 32.15 feet per second.
All right. People, if you're interested, try Tacori's precision measurement method, or maybe just try my precision measurement method with the car battery and the super slow-mo on your phone off of the parking ramp. And some people have said don't do a car battery, but I don't know. I think that's a great idea. Maybe you want to do something else.
If they say don't do a car battery, that person's supposed to have the same mindset you have. It shouldn't even matter.
I think they were maybe suggesting not to do a car battery because of safety issues. But to hell with the safety. Do it. This is science. This is damn science, people.
You gonna digest to prove gravity? Okay, so check this out. Listen. I remember you said something about the friction. And that's what's one of my points. One of my points was that the reason that the 9.8 meters per second square don't happen because of friction, because of objects grind in the air, and it slows that acceleration down.
Yeah, they grind in the air.
That debunks gravity. That debunks that 9.8 meters per second square. Because gravity gravity is the only force that's always getting debunked by other forces naturally. So meaning we know that friction is natural because of resistance. Friction is due to resistance. Based off the amount of resistance of object have, it'll determine how fast it will fall or accelerate. You know what I'm saying? So if a piece of paper has no mass, so it don't have no resistance. So it'll barely get any friction.
Paper has mass.
I said it barely have any mass.
Yeah, it doesn't have much. Okay,
let's put it like this. Charmin Ultra Soft Tissue. One strip. Charmin Ultra, that's a tongue twister to me. So excuse me on that one. Charmin Ultra Soft.
There you go. Just one ply even, right? Just pull it apart.
Just one little strip and just drop it.
Yeah.
And you ain't going to get 9.8 meters per second because of the mass of it debunks that. The less mass it has around the medium that it's in, the less resistance it's going to be able to have from the air that is in.
I see where you're going with this. All right, let me address this. So I did earlier say you have to control for confounding variables, and it is possible. And I know some people sometimes don't think this is possible, but it is in fact possible to have multiple forces act on an object simultaneously. So when something is falling through the air, gravity can act on it, and air resistance can act on it, and buoyancy can act on it. And if it's charged and it's an electric field, then the electrostatic force can work on it. All these things can work on it. You sum all of them together. Each of them has a vector. You sum the vectors and that's what you get. So if you want to isolate them, then you need to do things to isolate them. So if you wanted to get it so that air resistance wasn't a factor, then instead of using your 1-ply Charmin, you'd use a battery, a car battery, because its wind resistance will be very small in comparison to its downward acceleration force. So
Yeah, it has.
there you go.
I had dropped it and I had did a measurement from a 16-foot building. And yeah,
did
from
you
a
get on
16
video?
Did I get it on video? Yes, in my other phone. I'll send it to you. Listen. Let me show y'all something. I had my presentation, but I just can't even access my laptop. So I have my presentation, and yeah, this was your demise right here. So I had my presentation, just to let you know. So but
All
yeah,
right.
so check this out. So I dropped it. I dropped a few heavy objects actually. I dropped the bowling ball from 16 feet high. I dropped it from 16 feet high, and it literally took like 2 seconds.
So now,
2.074 seconds
but
from 16 feet.
Yeah, but now when you first let it go, what was its velocity when you first let it go? Immediately after you let it go.
Well, it
Its
accelerated.
velocity. Yeah, but what's its velocity immediately after you let it go?
When I let it go, the velocity it was actually 8.75, not 9.8. It didn't accelerate 9.8 meters.
The answer is zero, Tacori.
No.
The velocity.
Are you talking about like
immediately
right when I dropped it out of my hand?
Immediately after you let it go, its velocity is zero.
No, listen. When you let it go, it automatically started moving.
It does, but at that very instant, when you let it go, its velocity was zero. Now, 1/2 of a second later, how fast is it going?
How fast was it going? Well, in 1 second.
1/2 of a second. 1/2 of a second later.
Okay. Well, it was around 4.375 meters. It traveled that much. 4.375 meters.
In half a second?
In half a second. 8.75 meters in a second.
But I said,
which debunked that. That was debunked, bro.
What was its velocity? Velocity 1/2 second after you released it.
I just told you. Like I just told you.
No, you gave me an answer in meters.
4.37. It traveled 4.375 meters.
Meters is not a velocity. It's not a measurement of velocity. You're looking for a something that's measured in units of velocity.
Yeah, it actually is, because when a body falls, it travels 9.8 meters. The velocity for zero will be 9.8 meters according to y'all in 1 second. The second, it was 19.6 meters. Then the third, it was 29.4. Then the fourth, it was 39.2. That's what it was supposed to be, but it wasn't that in half a second. It was 4.375.
4.375 what?
Meters that it traveled.
Meters is not velocity.
No, I'm saying like what I'm reading off here. Like, let me show you.
Oh dear.
You see that?
Yeah.
Got the velocity.
Okay.
So I don't know what you're talking about. This was supposed to be like the velocity right here.
What are the units?
The units, meters.
No. Velocity is not measured in meters.
No, I'm showing you right here. The velocity.
I know you're showing me, but I'm saying velocity is not measured in meters.
I'm letting you. I know it's not measured in meters. I'm just saying how much it hit in the ground, not the velocity. I don't know how much was the velocity, but I'm telling you in meters how much it traveled in a specific amount of time.
Okay. And you're claiming that it's not the amount of time that is predicted by gravity.
Mm-mm.
The problem is,
it actually was with the bowling ball. It was 1.5 meters earlier.
Meters is also not a unit of time.
No, listen. I'm saying in 1 second. In 1 second, it was 1.5 meters under 9.8 meters.
So, do you think that in 1 second it should move 9.8 meters?
According to y'all, yes.
No, not according to me. No, its initial velocity is 0. It needs to accelerate up to 9.8 meters per second.
In 1 second, right?
So at the end of the first set, at the end of the first seconds, no, just let me tell you this. At the end of the first second, its velocity is 9.8 meters per second. It has not moved yet 9.8 meters because it hasn't been traveling at that rate the entire 1 second. It's been traveling at less than that for that second. You get that?
So listen,
I'm trying to explain it to you. I think you can get it, Tacori.
I get that. That's what I'm saying. That was the problem with the 9.8 meters per second. That's what I was saying. That's the problem with it.
Yeah, that's its velocity after a second.
In 1 second, in 1 whole second.
Yeah.
And this is accepted by many scholars. In 1 whole second, that thing is supposed to fall and travel 9.8 meters.
No,
downward.
it's not. No, it's not.
Yes, it is.
There's no scholar that says that. There's no scholar that says that. Because
at the end of 1 second, hold on. In the end of 1 second, the object wouldn't be travel at 9.8 meters in downward acceleration, right?
Here's a different maybe way to think of it. All right, let's say you get in your car, and
right. Are we talking about?
Yeah, just a second. I think you might get this better, right? Let's say you get in a car, and you want to accelerate up to 60 miles an hour, and you want to do it as fast as possible. Right? Mm-hmm. So 60 miles per hour. So you get in the car and you step on the gas, and it takes you 75 seconds to get up to 60 miles an hour. Right? Because that's the car you drive, right? So let's say that happens. Now, have you traveled 60 miles at the end of 75 seconds?
Have I traveled 60 miles at the end of 75 seconds?
Yeah. Because you're now going 70 or you're going 60 miles an hour, but have you traveled 60 miles at the end of that 75 seconds?
So we're talking about the downward acceleration of an object that's
and so I'm trying to use an analogy which completely maps, because when you get in a car and you step on the gas, you are accelerating from 0 velocity to a non-zero velocity. When you drop something, it's at 0 velocity and accelerates to non-zero velocity. So I'm trying to give you this analogy here so you can understand that just because you're going 60 miles per hour doesn't mean that you went 60 miles. You went from 0 to 60.
So according in a certain amount of time, right?
Yeah.
Okay, so in 1 second, right? The object would do what? The velocity would go from 0 to 9.8 meters, right?
It's the speed you're talking about, the velocity.
From
not
0
the distance.
To 9.8.
Yeah.
From 0 to 9.8.
I think you should stick with this car analogy. I think it's a good one, and it'll help you understand it better.
Isn't the 9.8 in meters?
It's meters per second.
Yes, so it has a distance and a time.
Yeah, it's a velocity, not a distance. It's a velocity.
And velocity equals d over t, right?
Yeah.
Okay, so velocity will require distance.
Yeah.
And it will require time. So I'm talking about the distance also, because y'all gave a consistent time and distance that an object is supposed to follow due to gravity.
Yeah.
9.8 meters is the distance, and the time is the second. Then y'all squared it. It's a second every second, meaning that the next second, in 2 seconds, it would travel it would accelerate double its speed from the first second.
It doubles its speed. At the end of 2 seconds, it's going to be going up almost 20 meters per second.
19.2.
Yeah.
That's what I had.
Yeah.
Come on, man.
So here is I'll jump right to
just said this
Corey. I'll just jump right to it here for you. You could run this through some kinematics if you wanted to, but the answer is the prediction of gravity is that the penny at the end of after 1 second of time, it will have traveled 4.9 meters. That's the prediction due to gravity.
In 1 second. That's why I was telling you earlier about the 4.9. So you said in 4 seconds, in 1 whole second, it would be 4.9, right?
4.9 meters is the gravity prediction of how far it will have traveled.
In 1 second, right?
Yeah. Yeah.
Well, that's a lie because 4.9 seconds is how much is 4.9 meters in feet?
Let's be sciencey and stick in
Yeah. How much meters? How much is 4.9 meters in feet?
well, it's about 3 feet to the meter. So you're
No,
looking at
no,
about
no, no,
15. You're looking at about
no,
15
no.
feet.
4.9 meters equals 16.075 feet.
Yeah, my rough approximation was 15, so pretty good. Pretty good.
It's not pretty good. It was off by 1 whole meter.
Yeah, 1 whole
You
foot.
as a globe earther who's supposed to be this big time mathematics, you wasn't supposed to. You were supposed to at least
Tacori. We do science and metric. Doing conversions from metric to imperial isn't a test of anybody's ability. That's not a big deal.
Okay, I know I'm joking with you. I'm just trolling. But it's 16.05 seconds. I mean feet.
Yeah.
Yeah, feet in 1 second. Well, guess what? Like I said, that bottle cap that I dropped, and I counted 1 whole second, and it took 1 whole second to drop from my head to my toe.
Tacori, you need to measure that to tenths of a second at least, and you can't do that by counting 1 Mississippi. That's not going to be precise enough, buddy.
Listen. Actually, it will be precise enough because each syllable takes 0.25 seconds to actually say. You know what I'm saying? Meaning that it actually almost dropped like around 18 inches.
I know what you're saying, but I'm gonna say, look, do a better measurement. I don't think that you're gonna convince. I don't think you're gonna convince anybody that your 1 Mississippi count was close enough.
Even check this out. Even if the 1 Mississippi, because 1 Mississippi, that's 5 syllables, right?
Oh my gosh. Are we having this conversation about how to measure time by counting 1 Mississippi?
You know, we always counted Mississippi to get a second. 1 Mississippi.
I know when you're rushing in touch football, you gotta wait to 5 Mississippi, right?
Yeah, 5 Mississippi, which is 5 seconds.
Yeah, but I prefer to play ultimate frisbee, and you get a stall count up to 10. You know that?
So y'all got different types of seconds.
Yeah, but nobody does. Frisbee. I'll tell you, in ultimate frisbee, nobody's doing Mississippis.
All right, let's pull it back in.
No, we talking
is globe. And also, we are going to be talking about gravity, of course, guys. And that's kind of where we want to keep things headed. But it's always, like I say, it's cool to be personable on the show. Honestly, sometimes these conversations get way too serious for, 2 people that are just trying to have a friendly exchange online. So let's carry on.
We was talking about the subject. We was talking about measuring the seconds and our perception on seconds because it's dealing with the 9.8 meters per second in a downward acceleration of gravity. And he was using his seconds on football or whatever.
Ultimate
just
frisbee,
showing to demonstrate ultimate frisbee. But I'm saying that.
Well, Ryan was here. He doesn't need a review of what we just had in the conversation.
Okay. So a second is always a second, and and gravity is supposed to be 9.8 meters per second. Like I said, that's not tested and that's not proven nowhere. There have to be a certain amount of mass in an object for it to be 9.8 meters per second, and then accelerate 4.98 meters. Or 4.9 meters, if you want to say 4.9 meters at the maximum second.
Yeah. So, do you want? We could go over the application of kinematic equations to see the actual prediction of gravity if you want.
The actual prediction of gravity.
Yeah.
You want to
go over the kinematics?
I want to go over some experiments because that torsion balance experiment, I want to talk about that too.
Oh, all right. Let's talk about the torsion.
You're not going to get away with that torsion balance
all right,
too.
Let's
but we don't talk about that in a little bit. We still going to talk about the 9.8 meters per second because we still got enough time. So, we know that like I said, that don't happen because you have to account for the friction. Not only do you have to account for the friction, you have to account for the resistance, which is also dealing with friction. You have to account for the mass, you have to account for the medium and
Yeah.
other things like
Yeah.
that, which debunks all that because it actually alters the speed of that something falls.
Yeah, you have to take those into account. It doesn't debunk it, it just makes it so that you need to account for it. And it can
It
reduce your
debunks it.
precision if you don't do a good job.
Debunking means that it completely opposes it and it completely like destroy the concept of it.
Well, I mean, you're gonna have to make a case better than just saying so. So, but you want it?
Well,
Is this in the torsion bar? Or are you talking about something else?
the Cavendish experiment, period.
Okay,
Because I had
the
looked at
the one I showed from Stephen Mold, right?
yeah, any of them, just any of them.
Yep. Okay. So what is wrong with the torsion bar experiment? What specifically?
Okay, well, there was one specific experiment that I looked at on YouTube, and they took a torsion balance and they put two lead balls on each side of them.
Yeah.
Two lead balls. They timed it, and it took like I think like a few hours for these lead balls to, I mean,
To stop
be
oscillating. Yeah.
to pull to each other, right?
Yeah. Well, typically it can take a
doesn't-
long time to stop oscillating if they don't have a dampener.
How is this responsible for curving whole planets into a sphere?
Well, that's a whole different thing. If once we've established that, then we can talk about the process by which it does that. So let's talk about it. What is wrong with the torsion bar experiment in your opinion?
The problem is that it doesn't prove gravity. It actually proves momentum.
It proves
Doesn't
momentum.
It proves momentum.
Okay, so
let's talk about this already.
All right, let's start with this. So you have I showed the video that had the two small masses inside that isolated chamber and the two large masses on the outside, and they were at rest. So momentum is zero, right? When they're at rest, momentum is zero.
Yeah.
I just need to confirm from you. Okay, so then the large masses were brought into place, and remember the small masses are inside of an enclosed chamber, so no air is able to interfere with it. They're all electrically grounded, so they're all at the same electrical potential. And lead is diamagnetic, which is so it doesn't carry its own magnetic charge well. Really, it doesn't, and it was repulsed by a magnetic field. So if there's a magnetic field at all, it would push the magnet or the lead masses away, not attract them. So they did that. They put the larger masses in there, and it attracted the smaller test masses toward the larger test masses. So what's wrong with that? What was going on?
Well, here's the problem. Like I said, with the torsion balance, because there's multiple ones where I actually saw. Because
let's talk about the one I brought up instead of some other one, right? Because I presented that as evidence. So it really makes sense in a debate for you to address the evidence I brought instead of the evidence I did not bring, right? That makes sense,
right. Well,
right?
We can actually look at the video together and we can actually debunk it. You know what I'm saying? Because
Oh. All right. I can.
Because it was kind of breaking up on my stream.
Okay, well, I can share it here. I'll share. Here comes Ryan. 3, 2, 1. There you go. Do you see it, Tacori?
Yeah.
Okay.
You're up.
So what's wrong with how this setup is? What is not going correctly?
You gotta play the video, bro.
All right, I'll play the video. All right, so here we go. This is the diagram, or we see what it looks like there. It's got the torsion wire on the inside, right? And there's the test masses inside, and the right. So what's going on wrong here, according to you?
Okay, I'm trying to look at the video. The problem is that this does not explain how gravity is. It doesn't explain how gravity can cluster objects into a sphere.
Well, I'll be
like
glad.
planets.
Look, I'll be glad to talk about that after we address this particular experiment.
Yeah,
So,
that's what we're
so this
talking about
particular
because
experiment is a test whether or not mass attracts mass. So, are you saying that this experiment does not show that mass attracts mass?
it
And if
attracts
so,
mass.
that
Listen,
then what's wrong with it if you think so?
I'm trying to tell you. I'm
Okay.
trying to tell you. Like I said, it actually deals with momentum. But here's the thing:
But
gravity. That because wait a minute, because that experiment is intended to prove gravity. It
it's a
can't just prove one part of gravity. It's supposed to prove every aspect of gravity. It's
there's
supposed to
just
explain every
yeah,
aspect of
mass
gravity.
attracting mass
The,
is what it's
the,
testing.
the
Yeah.
orbital, not only just that, but the curving bodies into a sphere
Sure. We can
and
talk about that after
and
we
other
address
things.
this experiment.
No, we addressing it. We addressing it. What this experiment, since it's gravity, and gravity is also the reason why planets are curved into a sphere.
Yeah,
How
yeah.
do this prove that part of gravity?
Yeah.
Of
Well, of
planets
course
curving into a sphere.
that's a different part. So we do it one step at a time. So does this, yes or no, does this show that mass attracts mass? And I think it does, and you think it does not. So what part of this contradicts mass attracting mass in your opinion? And
Well,
where?
mass attracting mass is magnetism.
But I already showed that magnetism doesn't attract mass.
Oh, it does? Hold on. So it don't have an attractive force?
It does, but it doesn't attract mass. Magnetism attracts specific materials based on particular properties inside the materials.
And actually,
And some materials are repulsed by a magnetic field, so it's completely
didn't
different.
attract it. It didn't attract it. What it did was, like I told you, it was the momentum. You know, even though the momentum was at rest, it still could be in motion, which caused it. It
So
still
how
can eventually, the torsion balance could still eventually get into motion. You know what I'm
and
saying?
how is that going to happen? How is momentum going to be imparted on the torsion bar by the test masses being moved into place?
Listen, I did a little demonstration a while ago. Well, I ain't gonna say a while ago. It was like, well, it's pretty much a while ago. It was like 2 months ago. And what I did was something just like that, like a torsion balance. What I did was I took a large stick I took two sticks. I had one that was connected to both of the trees, and I had one of them that was vertical in between the trees where it didn't touch. You know what I'm saying? And I came back and it actually one of them was actually more lenient towards the other part of the tree. It wasn't because of gravity, but it was just because of that momentum due to that torsion balance, or that torsion in the
I'm
string that it was hanging on. So it didn't
okay,
have nothing to do with gravity. It had something to do with momentum.
but
The
Tacori,
momentum can
I'm
change
not
also.
talking about that, Tacori. I put it on screen. You asked me to put it on screen. What about this particular thing
That's
is,
what I'm
in your
saying.
opinion, incorrect?
That's what I'm saying. It's incorrect. The reason that it's like I'm not denying the fact that it actually one of them that they was also actually brought to each other objects and other things like that. But I'm saying that it's not because of gravity. It was due to the fact of momentum.
Well,
You know, momentum
how is momentum doing that in this case?
because momentum can change, even though it could be at rest at zero. It could change over time due to
Due to
an
what?
interfering force, due to
What?
the interfering force
Yeah,
or the
what
momentum
interfering force?
of the torsion balance.
But how did that happen in this experiment? How did that happen?
It's the
You
string.
can't just say, I think it happened. I mean, you need to actually have a hypothesis for what you think actually
I'm
did
giving
happen.
you a hypothesis.
Okay, what is the force?
Let me show you something real quick. Let me show you something. I'm gonna show you exactly what caused them to do that. I'm gonna show you exactly what caused them to do that. Can y'all see Can y'all see me real quick?
I can see you on screen, yeah.
Okay. You see this line right here? You see this line right here?
It's off screen.
Oh, my bad. You see it?
Yeah, okay. The wire that's holding it up, the torsion wire?
Yeah, the torsion wire.
Yeah, okay.
The torsion wire is responsible for these two lead balls actually touching each up being attracted. I ain't gonna say attracted, but being moved to the other objects.
The torsion wire. So But before, this is the thing, Tacori, before the test masses were moved into place, the momentum was zero, that they were at rest.
I tell you what, can this happen? All right, like check this out. If I put 2 lead balls on each side of each other on a stick,
okay,
yeah, and I just laid them on the ground.
yeah.
Would that stick eventually touch those or be pulled to those lead balls? Without the string, without none of that, I just take a stick and 2 lead balls.
And you put the stick on the ground.
Yeah.
Yeah, there's other forces at play, Tacori.
Okay, that's what I'm talking about.
No,
there's other forces at play with this one.
Yeah, but this experiment here that I'm showing you isolates away those forces. So the stick sitting on the ground, for example, well, the resistance between the ground and the stick will be at play.
Isolate other forces.
Yeah. So here
isolate other natural forces.
Yeah. So here we have. Just a sec, Tacori. Let me explain. Tacori. So here we have inside that sealed chamber, we have the bar that's supported by the wire. And before they move the test mass into place, they wait for it to come to rest. So it's not moving. It has a momentum of 0. And it'll sit there forever without moving. So then they move the test masses into place. And because it's not a stick sitting on the ground, it doesn't have the resistance to the ground. The only thing that it needs to work against to twist that torsion bar is the torsion resistance of the wire, which is very small. So that's what's the only thing it has to.
But it still needs the wire though, right?
Yes, it doesn't just hover with nothing
don't
there.
Don't you think it was because of the wire?
Because gravity will pull it down. No, it's the wire is working to stop it from twisting, yet it still twists.
Listen, if you didn't need the wire, why don't y'all just take a long stick, like I said, take the long stick, because I know you said other phenomenons is actually dealing with that.
Yeah.
That means that gravity only work on, y'all gotta build something, y'all gotta build some complex stuff to make gravity do that.
No, it's to measure it's to measure the magnitude of gravity. That's what's happening. That's why they need to have a good apparatus.
So with all these things like the apparatus, the strings, and other things like that, just the 2 balls and the darn stick and the torsion.
Yeah.
Not the string, not the wire, none of that. You just lay the torsion, the wire the torsion to the ground.
The stick
and
on
you
the ground.
both of the lead balls on each side.
So why do you want to do it that way, Tacori? Why do you want to decrease the quality of the experiment? This is a high quality experiment. It sounds like you want to make it into a junk experiment. Why?
No, I'm not trying to make it into a junk experiment.
Let's do a good experiment.
I want to see if gravity is how sufficient gravity is. I just want to see how sufficient gravity is.
You want to know how powerful it is, the magnitude of gravity.
I want to see if gravity because I'm saying that the wire is the reason why the torsion balance was able to lean on each side of the leg.
Well, all right. Well, then,
the leg ball.
So then I have a very important question for you then, Tacori.
I wasn't finished.
Why did the wire twist when the test masses were put into place when it didn't twist when the test masses were not there?
You say the wire, why did it twist?
Yeah, why did the wire cause the twist, according to you, when the test masses were put into place?
Because of momentum.
There was no momentum. It was already 0. So why did
like I said, the momentum, even though the momentum was at 0, it could change over time.
Yeah, but
the momentum can change over time.
You need a force to change that. So what's the force?
What was the force? It could be something like the medium that is around, like the wind.
But there's no wind. It's in an isolated chamber.
Or the air.
It's in an isolated
and not
chamber.
Not only just that, but the mass of the torsion balance also to the wire. Because mind you say the wire is very small. So the torsion.
So you're saying the mass attracting the mass of the test mass is attracting the mass of the torsion wire?
The mass of the wire.
Yeah.
Due to the mass of the torsion. Because the wire is very small and it doesn't have enough force to deal with the mass of that torsion. The wire is gonna create momentum and cause the lead balls to be move to each other. This can't happen without this wire. This can't happen without
But
this wire.
I'm still asking you, and you're still not answering me. What is the
I
force
just
that's
answered.
causing it to twist? What's the force that's causing it to twist?
I just told you momentum. Why
Momentum
is it
is not
that
a force.
hold on,
A
wait a
change in
minute.
momentum requires a force.
Hold on, wait a minute. Because you should be able to do this without the string. You should be able to do the Cavendish experiment without the string, like I was saying.
Well, no,
Gravity only works
there's a
when
problem.
gravity.
Let me
tell you
finish his thought there.
Okay.
Gravity. Oh, okay, my bad. Go ahead.
No,
it's
go
on-
ahead.
it's
I
on
was
you.
giving you the floor there.
Yeah, you go.
Oh, gravity needs the torsion. I mean, gravity needs the wire and the balance to move the stick to each of the lead balls. But without that, gravity ain't doing that. Gravity like, oh, there's no wire, I'm not working at all. That's what gravity do. So it's not the so. I mean, using logic, it's the string, it's the wire, because the wire it wouldn't do that without the wire. That's just point blank. Period. If you take a ruler, hold on, I'm almost finished. I swear
Okay.
I'm almost finished. If you just take a regular ruler, 2 basketballs, you put the ruler vertical in between 2 basketballs, you leave and you come back, and there's no wind, there's nothing there. Gravity would not touch that darn ruler or move that ruler at all.
Are you done?
I'm done.
All right. You still have not answered. So let me remind you. In order to have a change in momentum, you need to apply a force. So the test masses there that are on the outside are moved into place near the torsion bar on the inside, and then it twists. But it doesn't twist before. If you don't put those test masses there, the torsion wire doesn't say, I just want to start twisting now. It doesn't happen. It requires the one variable to be changed. The independent variables changed of the position of the test masses. That's the only thing that changed. So how is it that you think the wire and or momentum somehow is what's causing the bar to twist when and only when the test masses are moved into place?
Because of the weight of the torsion and the weight of the wire. The wire is very small and it's not enough to keep the torsion stable.
Well, you've made my case for me. Thank you for that.
I didn't make your case. So tell me how I made your case. Because you can't prove this without that wire.
The wire is an important part of the apparatus to isolate
it's an
from
important
compounding
part
variables.
of the apparatus to try to make gravity real. That's what it is. Because it can't do that without the wire.
Without the wire, it falls down because of gravity.
No, it doesn't. It fall down because it's density.
All right. So go ahead, Ryan.
I was gonna say we can end the screen share and maybe move.
Sorry,
another realm. That's all right. Just while you guys were talking about it, it was fine. But just want to remind everybody, we will have a Q&A shortly. If our speakers have any other paths that they want to discuss, there's been a couple little skips and blips tonight, so hopefully our speakers are okay to stay this extra time, Mike and Tacori.
All right. Can I? Thank you, Ryan. Tacori, can I ask you this? So in our while we were talking in our chat, days and weeks ago, we talked about this topic, and you said, when I said, will you provide the mechanism that causes the 9.8 meters per second squared downward acceleration? It was a very specific number. I went over how gravity predicts that, but I asked you, would you do that? And you said yes. So you haven't yet. So I think it's fair for you to have a chance to show how whatever it is that you think causes things to go down, does it at that specific magnitude.
You said to account for the 9.8 meters per second squared?
I said that predicts the specific magnitude.
We don't give a specific prediction of a magnitude. We just know that objects accelerate more due to the resistance of the medium that it's in. And not only just that, but the amount of mass. So it accelerates.
Yeah, I say it's the amount of mass. Yep. I'm with you on the amount of mass there, buddy.
Listen, mass consists of matter, and a matter is the amount of space something takes.
Mass is not the amount of matter. Wait, what did you say? The amount
I
of space?
said mass consists of matter.
Yeah, mass consists of matter.
Okay, and matter is the amount of the amount of space something takes.
No.
Something like that.
All right, good. Just punt, I guess. All right. So, but you did say, and now you're not, and so I'm confused now. I'm very sad. You said that you were going to explain the specific magnitude of 9.8, and now you're not?
Why would I explain something that doesn't exist?
It does. We can measure it. It's measured all the time. It's used in engineering.
We literally just
every day.
That together.
You cannot build a building without including the specific 9.8 meters.
9.8 meters per second squared.
Yeah, downward acceleration. It's used everywhere. It's used so much. It's an absolute unchallenged necessity. Trying to claim that the downward acceleration is not 9.8 meters per second squared is a ridiculous thing, and I would love to have you say it on record because it's funny, but I don't think you should.
Say what on record?
That you do you think that there is a 9.8 meters per second squared downward acceleration?
In some type of mass, I guess, but you said every mass. You said every object.
Yes.
I remember you said that a while ago.
Yes.
So
all objects.
So a feather, right?
Yes.
So have you ever seen a feather fall at 9.8 meters per second?
Yes, I have. And I have also seen it.
So every second, so hold on, wait a minute. So every second, because we know that that's not facts, because the feather is barely dense as the wind. Dense as air. So due to the fact that it's barely dense as air or have almost the same amount of density, that means if air moves at a certain speed, which is wind, it'll alter that fall. Sometimes that feather won't even fall till the wind stop blowing. You know what I'm saying? Which is moving air particles. You know, so that's a lie right there. I'm just gonna keep it a book with you. That's a lie right there. Feathers don't fall at 9.8 meters per second square. Bowling ball don't even fall that fast.
Are you sure?
No. Well, I'm talking about when you first let it go, the first few seconds. But then, like, it depends on how high you is. Like, if you, like, on a 70-foot tall building, maybe so. But it won't stay at 9.8. It will accelerate to another meter. Like,
yeah, I think you're confusing acceleration with velocity again. But here, I'll show you, Ryan. I'm going to share. I'm going to share my
acceleration is the change of speed, a change of motion or something.
All right. You see that?
You're up.
All right. Let me make sure. Yep. All right. So here is a bowling ball and a feather. You see that? And this is just like one frame after they were released. Right? So here you go. And they're moving down at the same rate. Look at that. It's pretty cool. So there it is. Both of them falling at 9.8 meters per second squared. Isn't that cool? Look at it go. So yeah, feathers
That's in a vacuum, bro.
There you go. We controlled for confounding variables.
Hold on,
Isn't that amazing?
That's in a vacuum with no atmosphere,
yes, bro. You nailed it.
But
That's
we
right.
in the atmosphere.
But Tacori, I said you need to control for confounding variables, and that's what this is doing.
So isn't we in the atmosphere?
We are, but that's a confounding variable. Look at that. Look at that. It's so cool how it does that.
You gotta take away the confounding variable to make that happen.
That's how you do science. To make that happen. That's how you do an experiment.
No, because when you're dealing with science, you're dealing with everything natural. You're not altering anything. You have to alter something. We're not. The Earth is not a vacuum, fam. We're not in.
And that's why you have
atmosphere.
That's why you gotta. Yeah, that's why you gotta control for confounding variables,
with
fam.
The atmosphere.
Come on, fam.
Show us that with the atmosphere, fam.
No, Tacori. That's what I said. You need to control for confounding variables. The air resistance is a confounding variable. And so you have two things at the same time affecting the feather. So if you want to know, well, what does one of those things do without the other, you need to get rid of one of them somehow. And that's what the vacuum chamber was doing. It's getting rid of the resistance due to air so that you can isolate it out. It's exactly how you do science.
You finished?
Yeah.
You don't, first of all, no, you don't isolate. You demonstrate. What you do is you demonstrate things in a reality. That's what you actually do.
That's what we
You
just
actually
did.
do the experimentation and you actually do the test. And what we mean by that, it actually have to be accurate with reality. You
Yes,
showed
yes, it
us
was.
a filter. Hold on, wait a minute. You showed us a filter and a bowling ball
Yes.
in a vacuum.
Yes.
And a vacuum only means that it has no action.
Confounding variables.
Wait a minute. A vacuum only mean that it has no atmosphere.
Yes.
So you had the fact that you had to try to take away something and try to alter the reality of what we living in, because on the earth we're living in an atmosphere. You had to take away the atmosphere to try to make this feather, and it wasn't even just one feather. It was multiple feathers, and it was a bowling ball in a yeah, my bad. I'm getting sleepy. Yeah, it's a bowling ball in a vacuum.
Yes.
But we're not in the vacuum on the earth. We're
Exactly.
talking about,
and that's why we have to do that.
Earth.
That's why we have to do that, so that we can remove that confounding variable. That's how you do it. It's science. You have one.
Hold on, wait a minute.
You have one independent variable. You remove the other one so that you can isolate just the one independent variable. It's beautiful. It's a great way to do it.
How did that? Because I was looking. How did you? Because when I was looking at the video, it didn't give us a specific meter or a specific distance that it traveled.
No, it did not. No, that wasn't.
It didn't. No, so how you know it was 9.8 meters?
How do I know that it was 9.8 meters per second squared?
Yeah, that video.
Well, we can. They have the extended clip, and we can count the frames, and look at the frame rate, and then do the math on it. If you want, we could do it later, but it's probably not the right venue to do the math on it. But yeah, let's do that.
Yeah, I'm pretty sure that it did. Okay,
I'm gonna just jump in right quick. I'm pretty sure I was picking up what you were putting down there, Tacori. How much longer do you figure you have here before you want to go into Q&A?
I mean, it's up to you.
Oh, okay. I just thought based on your comment, if you know, we did start a little bit later than we planned. If you were getting tired, then we can go right into Q&A. But if you guys want to continue, I don't want to. Yeah. All right.
Yeah, it's up to you. Yeah, it's up to you.
You guys carry on.
I just needed to take a sip of my coffee and stuff.
Like I said,
coffee all you want.
Like I said, Tacori is one of the best flat earthers at doing math. So Tacori, we can maybe count the frames and apply the kinematics equation to get the specific acceleration of that later. How about that? It's a good idea.
Yeah, I guess so. I mean, if you can't do it right now, then that's a problem.
It'll probably take half an hour to 45 minutes just to really get an accurate count of the frames, and then run through the kinematics and things like that. It's not really the right venue for that.
Well, how long you guys have? All right, no.
Yeah.
Honestly, no. It sounds like we can move into our Q&A. It sounds like you guys have reached the point where I think it would be great if the audience can help you guys launch pad into some new avenues, and who knows how long those could take based on the subjects you guys are going to bring up. So keep your super chats coming in, and we're going to whip right at them. LJ says, what's the proof of Jupiter's mass, size, and gravity? Mike?
The proof. All right, so the specific mass of Jupiter can be determined by the period and the diameter of the orbits of the moons. And there's multiple moons of Jupiter, so you can have a good number of tests of that and get a good standard deviation on that. So what was it? Mass and what else?
Just
And
bear
gravity,
with me here.
yeah.
Gravity, mass, and let me just scroll back up. I was just checking on our live chat. Yep, just size and gravity was the other two things.
Oh yeah, so size you can determine by how far it is away from us, and its angular size. That's one way to get the size as an example.
Any thoughts over there, Tacori?
Well, that's not demonstrated. That's not demonstrated. There's no real type of measurements of the size of the planets or the masses of the planets. But one thing about me that I do like to use their sciences against them, so they won't make no excuses and be like, "Well, that's not what our science says." Well, I'm showing you, so I don't believe that they got the actual measurement of the mass of the planets or the size.
Do you have the science for that?
Well, the burden of proof on you. You the one gave a
Oh.
specific
No, I
amount
just
of the.
I just thought that you said you were going to use science to debunk it somehow, but then you just said you would, but then didn't. But that's fine. I
Well,
didn't
here's the
really
thing:
expect
the
that you would.
science is based off experiments, observations, repeated tests, and
Yeah, exactly.
over and over. But if somebody says that the mass that you gave is not the mass, that's the opposing factor, meaning that I cannot prove a negative.
All
Yeah.
right, question was for you, Mike. So last word, or if you want to keep the open discussion
No,
going, you can.
that's good. We can move on.
All right. Next one coming in from LJ. Also, once again, I want to say thank you, LJ, for all your super chats and always being here, asking these questions, even when it's not related to flat Earth versus globe or gravity or any of these things. Always asking questions about space. So, yeah, keep asking questions. We appreciate it. It's fun. LJ says, why can't we isolate and measure slash control gravity?
We can. I just showed how to do that. You do it in an evacuated chamber so that you don't have the wind resistance to it. And then if you wanted to have more precision, you would do things like use a specific material that is less magnetic, for example, and then you would still demagnetize it. Things like that. But also the torsion bar experiment that I showed earlier is a great way to isolate it and show that gravity exists. So thanks, LJ.
I'll give you a chance to rebuttal there, Tacori.
Yeah, here's the thing: when we're dealing with science, we don't alter reality. We just demonstrate it in reality. So, like I said, due to the fact that we live in a medium and we don't live in a vacuum on in the atmosphere, we live in the atmosphere, which means he was supposed to show that in the atmosphere because he say, why do you fall in the atmosphere? But yet the experiment that he showed is isolating all of that. So you got to change reality to make gravity exist, to try to make gravity exist.
All right. Well, it was just a great way to have an independent variable. So there's just one independent variable instead of multiple. Helps the experiment to go better. So thank you.
All right, you got next one coming in from LJ as well. Why don't we have the remains of any asteroids ever?
Why don't we have the remains of asteroids? Well, there's plenty of meteorite hits in the Earth, and then around the craters there are samples of that all around, scattered around. So we do. Unless you're going to be very specific and say that those are meteorites, not asteroids, but I don't think you're caring about that. But anyway.
All right, chance to rebuttal if you'd like, to Corey.
Yeah, well, this is not Guardian of the Galaxy, so rocks don't fly everywhere. Rocks don't fly at all. First of all, these rocks are supposed to be in space, in a place that's supposedly a vacuum that has no medium. Rocks don't ain't supposed to be shooting from space to Earth because they don't have no medium to travel. They need air to travel. They need oxygen. They need some type of medium. And not only just that, but they also need not only just that, but we found that these meteorites actually move past bullet speed. So if these meteorites was actually real, then that means that you telling me that these satellites up there, they're actually doing like some type of ultra instinct and not getting hit by these rocks and things like that. And one last thing, those crater impacts, those are rock quarries due to the natural disasters of earthquakes and other things like that.
All right, and I do apologize to Corey, where these questions are for Mike. There are questions for you as well, where you'll get the first and last word, but last word for you, Mike.
Um, the satellites do get hit on occasion, but orbiting the Earth, but for the most part, there aren't a whole bunch of asteroids just floating around the Earth like that. Movies are just doing those types of things for visual effect. That's not reality.
All right. Next one coming in also from LJ. And then we have another super chatter. So don't worry, everybody. We'll, we'll have another super chatter. But we, once again, do appreciate you, LJ. How's gravity holding down oceans, but we can walk?
So gravity is proportional to the mass. If you look at the equation, G equals M1 M2 over R squared. So M1 is the mass of the Earth. M2 is your mass. And so your mass is a specific amount, 100 kilograms, for example, giving you a specific downward acceleration. And so you resist that by applying the same amount of upward force in Newton's, your leg muscles or whatever. And you can resist it because you have those muscles. Oceans lack muscles. There are muscles in oceans, but that's not the kind of muscle I'm talking about. They don't have the kinds of muscles like your legs do to keep them up. They just react to the forces that they have. So, but they do. Sometimes there's waves that hit each other and droplets of water shoot up, and they do resist for a while, but they're pulled down then still.
All right, the floor is yours, Tacori, to respond.
About the gravity thing and about first of all, like I said, this is why I brought in my first round when I say that mass, because if that's the case, then he have to explain why because gravity curves planets into a sphere, and planets have less mass than the Milky Way. How come the Milky Way ain't curving into a sphere also, but the planets are, which has less mass than the Milky Way, and curving the planets into a sphere? So that's a contradiction, and that's not always true. So that debunks that portion of gravity of needing more mass to be effective.
That's a great question, Tacori. And the reason why is because they're in orbit around the Earth or around the galaxy. And so the centrifugal force of the movement and the centripetal force of gravity are in balance with each other. That's why it's not all collapsing in immediately just straight in, because of that lateral rotational motion.
Okay, so that
debunks
gravity.
Good question.
All right, let's carry on. We have one more for you, Toon, and then we'll have a few more coming in here for you, Tacori. Brian Bender says, Toon, can you demonstrate mass equals mass in nature?
Mass equals mass? Is that what it says?
Can you demonstrate mass equals mass in nature? Trying to do it some credit,
I don't know how to parse that. Like the magnitude of one mass equaling the magnitude of another mass, you'd put it on a balanced scale and do that. Or do you mean mass accelerating or mass attracting mass? Well, I did in the experiment video that I showed from Stephen Mould. So that's mass attracting mass in nature. Nature being everything that's natural versus the supernatural, the metaphysical is the non-natural universe. So yeah, that was a good example of that. I hope that's what you meant.
Yeah, of course. I'll hand it over to you, Tacori. Maybe you can help out our super chatter here and explain. So they asked, Toon, can you demonstrate mass equals mass in nature? And it seems like we're a little bit confused about what our super chatter might mean here. So help us out, Tacori.
Well, he's pretty much meaning is that it was pretty much the same thing what I was saying earlier of the mass equaling mass, because based off the equation that I showed and that he demonstrated that I calculated, the mass of the force of gravity would equal the mass of the force of a person, and that's not real. You know what I'm saying? Because we don't have no type of weight or any of that, or we have all type of resistance and things like that. So that
Oh, I think he's
talking to somebody off screen.
That's it. That was it.
Oh, okay. No worries. Did you have anything else to say, Mike, there, or do you want to carry on?
No, that's all good. Units were weird, but
All right. Everything good over there, Tacori?
Yeah, everything good.
Okay. Just checking in. It seemed like there was somebody chit-chatting with you. I didn't know if there was any problems going on there. So let's carry on. Matters Now said, Tacori, can you stand up? Then you can lift your weight. MCToon, he said the moon sucks the tides. Please correct that. After show on Matters Now.
I said the wait. Tacori. All right. The question is to you, Tacori, not me.
You asked me. He asked me about the moons and the tides.
No, he embedded a secret message to me inside the super chat to you.
Can you ask? Can you repeat that question again, Ryan?
So he said, Tacori, can you stand up? And he's basically implying, if you can, therefore, then you can lift your weight. And then, so I'll let you answer that first part, and then we'll ask the second question. It's not really a secret question, but it is a
Oh yeah,
secondary
yeah.
question.
Okay, yeah. My bad. Here's the thing right here. That's only me picking. Like if I do that, I'm not gonna even exert half my weight. If I stand up, I'm not gonna even use half my weight. But we're talking about 200 pounds plus 200 more pounds, meaning I'll be using 400 pounds worth of force, dealing with 400 pounds worth of force total. Well, I'm 190, I'm not 200. So 380 pounds worth of force total. So I can stand up because I'm not using that much weight. And I don't have no force holding me down.
Okay. And the second part of that says, MCToon, he said, the moon, he implying you, Tacori, so you can clarify here. So Tacori said the moon sucks the tides. Please correct that. Or are you just trying to get me to say something really strange? I don't know.
I think Tacori earlier had mentioned the tides and got a little bit wrong about what the claim is. So
no. Listen,
I get worried every time I have to say sucks on air. Anyway, yeah. So go ahead, Tacori.
What I was saying that the moon, I was simply saying that moon's gravity is not responsible for tides, due to the fact that there's different type of, when you look at the model of the globe Earth model, you can see that wherever the moon is, the tides will be the highest at the equator. But when you look at the tide amplitude maps, the highest tides be actually at the borders. And then you got tidal nodes, meaning that there are no tidal activities in those areas, but the moon goes over in those areas too, where there's still tidal nodes, meaning that gravity will have to pick and choose what part of the water or the ocean they want to pull on.
All right. Any thoughts over there, Mike?
Yeah, I'll just that's definitely not what's going on. There's multiple factors in tides. A large portion of what causes tides to be higher or lower is the topography of the underwater surface there, not the surface of the water, but the ground under the water, the seabed. And so there are places where it's low, and you get that's what's necessary for the tides, because the water's rushing in. But if you have less vertical area, then more water goes in, and you have a higher displacement there. And then you get places like in I don't know if it's Nova Scotia there, where it really has these really high tides because there's basically a funnel of the water going in. So that's the explanation for the globe. I don't know what your explanation is, but I've never heard a good one. But from flat earthers, other than the very funny one from Eric DeBay that says it's due to the heaving of the bosom of the deep, just like hearing a bosom in a science talk is funny.
All right.
I don't know what Eric DeBay be talking about, but I'm going to give that one a thumbs
down to DeBay.
To you too. Hey, I got to use the restroom real quick. I'll be right back.
Oh, all right. Don't bring us with.
Oh yeah, you're right. No, detach your headphones. Don't be like that one person in what was it, Congress or something, that brought the whole drive people to the old restroom with them. Boy, that was something. All right, so everybody hanging out. This has been fun. We managed to get it going. It was a little bit late, but things happen. We have some internet glitches every once in a while, but this has been fun. And we got a few more super chats to go for sure. Maybe some that we can go through. Let's see. Michael King said, I won't say the name, but he said someone was a petulant child with their last debate. I will read that and just get it out of the way just while Tacori's gone, which is that if you do come to a channel with moderation, expect to have some level of moderation. And here at Modern Day Debate, it's more about letting people generally fall on their own sword. We want to try to keep things on topic, and if things sometimes stray a little bit, that can be okay. And we come full circle usually, but the whole point is, we try to let people fall on their own sword so that they can't run into their own spaces and say, "Oh, the only reason I didn't look compelling is because the moderator was being XYZ." There's I don't think that's going to be a problem here. You can debate that in your own circles, but I do my best to be fair. And I have friends across all thought spectrums in these spaces. And yeah, we'll just leave it at that. Let's see if there's anything else here that's not direct. Let's see. Matters Now came in for another $2. I will say again, MXXD is a moderator over there, or host, I should say, and fantastic mod in our chat as well. So thank you, MXXD. They're doing an after show over there. So they did ask a question for Tacori. We'll get to that shortly. I will remind everybody that once again,
I'm back.
20% off with your tickets. When you there's a link to Mindfest. You'll get 20% off when you use MDD as your promo code. I will once again put in our GoFundMe for our moderator Shane, who has had some medical emergencies recently, and anybody who can help out our good moderator Shane, we appreciate it. And lastly, before we go back into Q&A, we do have a Discord that is also handled by Hannah, MFXD, Shane as well, Anathema. Check it out if you want to get develop your debate chops. Let's carry on. And thank you, MXXD. Yes, appreciate you guys as well. All right, so Demon Stride says, MC Murhouse kills it again. Join discord.gg/demonstride for an after party. Seems like there's going to be a few after parties going on, so
I've got another debate in an hour and a half on my channel too. So you can do the after party, then come watch yet another debate. And then maybe they can do an after party after that debate.
Oh my, it's gonna be just a debate palooza. And then, of course, with us co-streaming the Minds Fest, if you haven't already, hit the notification bell. There's several debates that are already posted that we got ready to go, queued up, and you won't want to miss them. They're gonna be live events. It's gonna be great. So Megan Marie says, the fact that the penny fell at all proves gravity.
No, it don't.
Okay, go ahead there, Tacori.
There you go. How do you argue that?
What? The penny fell because of density is denser than the medium that is in, so of course it's gonna fall. It has more resistance. If the medium has less density than a penny, then the penny is gonna fall because the more mass that the penny have, or the denser the penny is, it has better resistance against the medium. So of course it's gonna fall. What in the world is?
Any thoughts over there, Mike?
Yes. Density is just a ratio between volume and mass. It has no direction, and it's not a force. So density cannot cause something to fall. That's all.
Okay. Joshua Jamie says, put a piece of TP on a book, they fall together. TP? Do you mean bum wipe? What TP? What do you mean?
If you take a book, here's what they're saying. You take
Shit tickets? What's going on?
You take a book like this. Here's my elementary surveying book. If you put that piece of toilet paper on it and you drop the book, which is isolating the wind resistance because the book is not as affected by the wind resistance as the toilet paper will fall with the book at the same rate. So it's a way to isolate the toilet paper from wind resistance.
Sorry, live chat caused me to exhale greatly. All right, let's carry on. Unless you had anything to inject there, Tacori. Oh, you're on mute, Tacori. Are you there? Let me just ask Tacori to come off mute. If you can come off mute and start your camera, I'm not sure if you're still there. But let's carry on. Maybe they're just having an intermittent issue. No worries there. Wade Eberly says, let's say you got in your car and you accelerated so slowly that it took an hour to get up to 60 miles per hour. How far have you gone in that time? 60 miles. You weren't going 60 miles per hour until the very end.
Good way to
You
put
asked
it.
him.
Oh, are you there, Tacori?
Yeah, did they ask me a question?
Yes, I can repeat it if you didn't hear.
Yeah.
Okay, so Wade Eberly says, let's say you got in a car and accelerated so slowly that it took an hour to get up to 60 miles per hour. How far have you gone in that time? 60 miles? You weren't going 60 miles per hour until the very end.
Okay. I mean, that don't prove the 9.8 downward acceleration, but whatever floats your boat, you know. I say it like this, that there's a certain amount of there's a certain amount of time. There's a certain amount of time that a boat actually falls. I mean, not fall. I'm tripping. I'm thinking of something else. There's a certain amount of time that the car hits its destination, certain speed, you know. But that don't got. I agree that it'll be 60 miles per hour and stuff at the end of that. At the end, but you know that don't got nothing to do with the 9.8 downward acceleration. We're not talking about a car moving. We're talking about an object falling.
Okay, did you want to carry on?
Nope. It stands alone. I have nothing. Nope.
All right, no worries. Well, let's carry on, everybody. And thank you so much for all your super chats. We appreciate it. Michael King says, what is the geometry of space? Its majority of existence. So I think, sorry, I'm going to try to rephrase this. I'm not sure if this is phrased right. What is the geometry of space? Its majority of existence. So I think worthy of looking into. Not a lot of pronunciation there, but
Is
yeah,
he, I don't know, is he
figure it out.
asking? He's asking about the geometry of space. Certainly, that is for Tacori. He can elucidate.
Sure thing.
Huh? The geometry of space?
Yes. That is the first part. What is the geometry of space?
That's all. He asking Michael that. He ain't asking me that.
You don't know the geometry of space?
Is he asking? What do you mean by the geometry of space?
I don't know. Sounds
So
like a good
they're
question
saying,
for you.
Michael King says, I think I've got this all figured out. Sorry, Michael. They're saying the geometry of space, it's the majority of existence. So I think it's worthy of looking into.
Okay.
Okay. All right, let's carry on then, everybody. Sorry, Michael. I think that's all we're going to get out of that one. I had to say geometry 3 times, you know. I'm gonna, you know what they say if you say that 3 times in the mirror, right? Anyway, no dad jokes. Max the Atheist, has Tacori ever appeared per se in court, like as a sovereign citizen with a parking ticket? What is this? No, we're just gonna move on from there.
Yeah, that's
nothing to do.
Yeah, that's an atheist. You know, we can't.
Max the Atheist, yeah. I mean, yeah. I saw the sovereign citizen part, and I was like, "What is going on here?" This is
I
I think they're just joking around.
That's why I don't conversate with atheists like that. You know, it's difficult to.
All right. Well, we won't get into the that right there. So sorry, we gotta move on. And I'll apologize to our super chatter. Behave. Matters now. Explain the Galileo law of free fall.
That's gonna be for Tacori.
Well, I never did like a lot of research on the Galilean law of free fall. I gotta do some research on that though. On that Galilean's law of free fall.
All right. Any thoughts on the other side, or you want to carry on?
No, that was good.
Okay. Jacob McGee, two lock boxes, says when you throw an object in the air, it stops so at zero velocity and then begins to fall by 9.81 miles
Meters per
second
second.
squared.
Yeah.
Yeah, sorry. How is this not an initial velocity of zero?
So
Remember my math skills.
the initial velocity is non-zero because it started by going up. But if you want, you can break this down into two separate kinematic equations. You can do the first half from when you threw up until it hits zero, and then the second half you can do from zero until it hits the ground. Run the kinematic equation twice on that if you want. So that's a perfectly fine way to do it. But the initial velocity is whatever it was upward when you released it.
Any thoughts on the other side? Or would you like to carry on, Tacori? Oh, you are on
I'm gonna
mute.
just let that go.
Okay. Oh, let's carry on. Even Lord, and we're getting down to our last two super chats. So thank you everybody once again that has super chatted. If you have any questions, get them in now because we're going to wrap up very shortly. MCToon, considering every society will have a religion and atheist societies don't reproduce, what religious society would you rather live under?
Well, number one, to my knowledge, atheists do reproduce, so I don't know why you would say that, but I don't know. That is a difficult question because I am not an atheist. I am a Christian. The problem is that there's an awful lot of Christians that are not awesome people. So I don't know if I would want to live in that particular society myself either. So I don't know other than to maybe invent some science fiction or call in some science fiction or fantasy society, but not even that. I don't know. That's a difficult one. I think for the most part, people should be able to choose their own religious beliefs and society shouldn't be pushing them on anybody.
Okay, any thoughts on the other side? Oh, you're on mute.
I would say I would rather not live as an atheist. I think it'd be better to live as somebody that has a type of belief system. Because when you actually check out the belief system of theist people and atheist people get everything from theistic people. You know, we gave them math, we gave them science, we gave them philosophy, we gave them logic. Everything that atheist people see right now that they're interested in, we already set that out for them. Even the ape-like ancestors, even mentioned in the Bible, they got that from us too. So it's best that you live as a theist, and plus we have morals and justice systems, and they don't unless they learn from under us or get something from us.
All right, sounds like something we can have a debate down the road with some of the people we host on here. I'm sure they're listening. So let's carry on. I think unless you have anything to close with there,
No,
Mike, I think that one was for
it's
you.
all good.
Okay. Last one coming in. Aaron Reese says, Aaron Reese, sorry, when you lift yourself up with your legs, why don't you have to provide a force in the opposite direction to keep from flying into the air?
That's for Tacori.
You know
That's
what?
for you, Tacori.
Yeah, you know what? I deal with that question like 1,000 times a day, so I'ma just not answer that. I'm sorry. Well, he's a super chat, so I'm gonna answer that question because I am denser than the medium that I'm in. I don't know, man. I, I don't know. You know, I already answered this question like millions of times throughout the debate. But I will answer that question again just for the super chat. That is due to density that keeps you on the ground. That's what it is, due to density. And not only just that, but we also got downward electrical currents that's also in our atmosphere. And this is tested and proven. You can literally go out and measure this. You'll be a fool if you say that this is not real. We got downward electrical currents that also keep us to the ground with density. That's it.
All right, two parts. Number one, the current is not downward. It's positive up and negative down, and there's no real direction to an electrostatic field like that. So it's not downward. Number two, density is, well, the laws of motion. If you are moving upwards, you shove yourself upwards, you have a velocity up. And if you do not continue going up, it requires some force in the opposite direction. Some force is exerting itself to stop you from going up constantly. Density is not a force, it's a relationship between mass and volume. Two densities together isn't a force still, and if you subtract them, all you get is a direction. You don't get a magnitude. And so the direction does sort of help you, but that only is about it really only relates to buoyancy and which direction buoyancy is going to exert itself. So it has no direction until, if you compare them, it has a direction, but it's not really doing you much good because it doesn't give you a magnitude. And you must do better at a magnitude than mass attracting mass does if you think that you're going to replace it. You can't even get into the horse race if you don't have a way to predict the magnitude. You showed up without a horse.
Any thoughts on the other side before we move into our closing statements?
No thoughts. I mean, no comment.
All right. You know how I like to go in the reverse order. So, Mike, 1 minute on the floor for you. Closing thoughts and where everybody can find you.
All right. Well, you can find me on MCToon Live or on Conspiracy Tunes. I do pre-recorded videos on Conspiracy Tunes on YouTube or mctoon.net. I have all my links there. Later tonight, I will be debating in about an hour and 15 minutes again, Cap and Hook. So thank you very much, Tacori. It's been great. I think Tacori is a good guy, a lot of fun to talk to, and definitely one of the flat earthers that has probably the best handle on math out there. So I think the other flat earthers could probably they all look up to you on how to do math. So thank you very much.
All right. Excellent. And 1 minute on the floor. And thank you so much, Mike, for your closing statement. 1 minute on the floor there, Tacori, for you. Your thoughts on our discussion and where everybody can find you.
Okay. My name is Tacori Dawson. You can find me on my YouTube channel. I just got it done up. Tacori Dawson, the Tacori Dawson Show. I already dropped 2 videos because I just started my show. I have another debate tomorrow. People could check that out. It's on Paradigm Shift TV 314 under DMG the Poet. I repeat, Paradigm Shift TV 314. That's why I'm gonna be doing the debate at. And also the Tacori Dawson Show, which is my own independent channel, and another channel which I also debated the brother MCToon on, which is pretty much called The Real Lions Den TV.
Yeah.
Yeah. You know who I'm talking about.
Yeah, they're great.
Yeah. So that's it.
All right. Excellent. That was perfect timing, actually. My buzzer was going off. So thank you to both of our speakers. A big round of virtual applause for our speakers keeping it friendly, really chill discussion, debate tonight. We had a lot of fun, I think. So hit the like button if you had fun. And once again, we had a few little blips here and there, but we won't pay attention to that. We got our last chance to purchase tickets for the live event, 20% when you use LED as a promo code for the Minds Fest. If not, hit the notification. We got several events posted already that are going to be posted live to our YouTube page here, so you won't want to miss those. And once again, we're going to be back in just a few days with other juicy debates beyond that as well, so keep a lookout for that. Once again, thank you guys, and we'll see you next time.